So tonight I will be reading chapter 21, or continuing my reading, I should say. Um, Pretty much the entire day today and yesterday, I haven't had any time to do any reading, but I did do a little bit of reading in the evening last night off stream, so pick up where I left off there, which is here. The book was talking about doing long jumps as a way of returning from signal handlers, and I don't see myself ever needing to do that, but I suppose it's a way that you can exit the signal handler. But let's continue on reading from the example program here. Alright, so listing 21.2 demonstrates the difference in signal mask handling for the two types of non-local go-tos. This program establishes handler for SIG-INT. The program is designed to allow either set jump plus long jump or SIG set jump plus SIG long jump. So there is a special SIG version of the long jumping stuff that basically I think it just monkeys with the masks. So when you exit the signal handler, you actually drop the mask that you had when you entered it. At least that's what I remember from the other night when I was reading this before bed. Alright, so it allows both versions to be used to exit the signal handler, depending on whether the program is compiled with the use sig set jump macro defined. The program displays the current settings of the signal mask both on entry to the signal handler and after the non-local go-to has transferred control from the handler back to the main program. When we build the program so that long jump is used to exit signal handler, this is what we see when we run the program. So just a regular long jump. The signal mask is empty. It calls set jump, and then we hit Control C to generate a SIG-INT. It says I receive signal 2 interrupt. The signal mask is for 2, and then after the jump after jump from handler, signal mask is still 2. At this point, typing Control C again has no effect since SIG-INT is blocked. Type Control backspace to kill the program, which will also core dump it, I believe. From the program output, we can see that after long jump from the signal handler, the signal mask remains set to the value to which it was set on entry to the signal handler. In the above shell sessions, we build the program using the make file supplied with the source code distribution in the book. -S option tells make not to echo the commands it's executing. We use this option to avoid cluttering the session log. Okay, when we compile the same source file to build an executable that uses sig long jump to exit the handler, we see the following. So this time we have it for the sig long jump. It's empty. We then hit Control C, we get interrupted, and we have it as part of our mask. And then after our jump, we're back to being empty. At this point, SIG-INT is not blocked because sig long jump restored the signal mask to its original state. Next, we type Control C again, so the handler is once more invoked. Yep. It receives the interrupt again. Yep. Cool. From the above output, we can see that sig long jump restores the signal mask to the value it had at the time of the sig set jump call. Listing 21.2 also demonstrates a useful technique for use with a signal handler that performs a non-local go-to. Because a signal can be generated at any time, it may actually occur before the target of the go-to has been set up by sig set jump or set jump. To prevent this possibility, which would cause the handler to perform a non-local go-to using uninitialized env buffer. That would be bad. We employ a guard variable can jump to indicate whether the env buffer has been initialized. I would just set up a mask immediately in the main, and then only remove the basket until after your long jump buffer is set up. If can jump is false, then instead of doing the non-local goto, the handler simply returns. An alternative approach is to arrange the program code so that the call to sig set jump or set jump occurs before the signal handler is established. However, in complex programs, it may be difficult to ensure that these two steps are performed in that order, and the use of a guard variable may be simpler. Note that using ifdef was the simplest way of writing the program listing 21.2 in a standards compliant fashion. In particular, we could not have replaced the ifdef with the following ratio check. This is not permitted because SUSV3 doesn't allow set jump and sig set jump to be used within an assignment statement. Basically what you expect. Terminating a process abnormally, abort. The abort function terminates the calling process and causes it to produce a core dump. The abort function terminates the calling process by raising a sig abort signal. The default action for sig abort is to produce a core dump file and terminate the process. The core dump file can then be used within a debugger to examine the state of the program at the time of the abort call. I just was curious before streaming. I looked up, like, GDB has this gcore command, so you can attach to a program, run gcore to dump the core of the program, and then resume execution. Just uses ptrace, and then there's an analogous gcore command that you can use outside of GDB as well. I've used it in the past and have had limited success with it. I guess we can see if it's installed here. Gcore. Yep. So if you have a running process, let's just do mkdir. This is going to be for chapter 21. And we're just going to say vim core dump me .c main. Just added a comment up here. This program loops forever, expecting to be core dumped with gcore. Alright, and then here we'll do pound include standard io.h just to get our print stuff, and then we need standard lib for the constants, and then here we say printf core dump me, add a new line so the buffer gets flushed, and then forever. I think you just do a while though, right? While true. While one. Do in here we're going to sleep for 1 second. Oops. Sleep for, let's go ahead and man up sleep. It's more thinking man 3 sleep. Unix standard.h. And it's in seconds, not in milliseconds. So we need to go just say 1, and then printf and then can we do man3 flush, f flush? Yeah, That's for files though. Man3 printf flush. Doesn't say how to flush. Let's go ask AI. When using printf with no new lines, how do you force a flush? Syntax thing is f flush. Standard out. Oh, I gotta give standard out. Okay. F flush, standard out. Sounds good. Oops. Jump over to chapter 21. Meant to kill that thing. And then CP chapter 20 make file here. Then make file. Okay, make and build core.me. Okay. And over here, actually I want to get the PID vim core.me. Which would be gcore. And then you give it the PID. So how about we do this? We do de like that. So gcore %d new line. Here will be get PID. Something like that. Okay. Make and then we can run gcore like that. Sudo bang bang. GitHub. Okay. Let's just run our gcore again. Gcore. So we got 1 tick a second. 1, 2, 3, 4. So you got a little bit of a slowdown there. Maybe like 2, 3, 4, 5, 6. Yeah, you can barely notice. Warning, memory read failed for core file section. How big are these files? They're not very big. 562K. I guess that's about right. Let's see. Let's guess. How do I load a core dump into GDB? I need a path to build that, and then core. Sorry. stack trace. So definitely can tell that we're in main. I don't really have any, maybe say registers. I don't really know how to use GB. I can say help. Help. Stack. Why does it say list of classic? BT frame. Alright. Kill it. Alright. The other way to get the core dump would be to say build that, and then I guess it control backslash, which quits it and gives a core dump in, right? Does control backslash send in a abort signal? Core dump CTL list, and then you can see, yeah, it was sig quit. There was a core dump here. Since a quick default action is terminate and produce a core dump, this is what feels like an abort sometimes. What the abort signal really is, abort signal is sig abort. It's typically generated by calling abort in C. Default action, a sig abort, terminate the process. So it has the same disposition as sig quit. Like sig quit and sig abort have the same disposition. But abort's typically internal. Okay, makes sense. The abort function terminates the calling process by raising sig abort signal. The default action for sig abort is produce a core dump file and terminate the process. The core dump file can then be used with a debugger to examine the state of the program. At time of the abort call, susv3 requires that abort override the effect of blocking or ignoring sig abort. Furthermore, susv3 specifies that abort must terminate the process unless the process catches the signal with the handler that doesn't return. The last statement requires a moment's thought of the methods of terminating a signal handler described in section 21.2. The one that is relevant here is the use of a non-local goto to exit the handler. If this is done, then the effect of abort will be nullified. Otherwise, abort always terminates the process. In most implementations, termination is guaranteed as follows. If the process still hasn't terminated after raising sig abort once, i.e. the handler catches the signal and returns, so execution abort is resumed, abort resets the handling of sig abort to sig default and raises a second abort, which is guaranteed to kill the process. If abort does successfully terminate the process, then it also flushes and closes standard IO streams. An example of using abort is provided in error handling functions of listening 3.3 on page 54. Okay, this is the cool stuff, the sig stack stuff. Handling a signal on an alternate stack, signal T or SIGALT stack, I should say, SIGALT stack. Normally when a signal handler is invoked, the kernel creates a frame for it on the process stack. However, this may not be possible if the process attempts to extend the stack beyond the maximum size possible. For example, this may occur because the stack grows so large that it encounters a region of mapped memory or the upwardly growing heap. Really? You can encounter the upwardly growing heap? Figure that'd be like impossible. Or reaches the R limit stack. 64-bit addresses, that's gonna be exceedingly rare. Or it reaches the R limit stack resource limit. Okay. When a process attempts to grow its stack beyond the maximum possible size, the kernel generates a sig-seg-v signal for the process. However, since the stack space is exhausted, the kernel can't create a frame for any sig-seg-v handler that the program may have established. Consequently, the handler is not invoked and the process is terminated. If we instead need to ensure that sig-seg-v handle is handled, in these circumstances we can do the following. Allocate an area of memory called an alternative signal stack to be used for the stack frame of a signal handler. Use the signal stack system call to inform the kernel of the existence of the alternative signal stack. When establishing a signal handler, specify the SA on stack flag to tell the kernel that the frame for this handler should be created on the alternate stack. A signal stack system call both establishes an alternate signal stack and returns information about any alternate signal stack that is already established. Okay. The sig stack argument points to the structure specifying the location of and attributes of the new alternative stack. The old stack argument points to a structure used to return information about a previously established alternate signal stack, if there is one. Either one of these arguments can be specified as null. For example, if we find out the existing alternative signal stack without changing it, by specifying null for this sig stack argument. Otherwise, each of these arguments points to a structure of the following type. So we've got a void star, which is a pointer to the starting address of the alternate stack. And then we got a size, of course, size of the alternate stack. And then we got some flags. On stack and SS disable. The SSSP and SS size fields specify the size and location of the alternative signal stack. When actually using the alternate signal stack, the kernel automatically takes care of aligning the value given in SSP to an address boundary that is suitable for the hardware architecture. Typically, the alternate signal stack is either statically allocated or dynamically allocated on the heap. SSV3 specifies the constant sig stk.sz to be used as a typical value when sizing the alternative stack, and min sig stk.sz as a minimum size requirement to invoke a handler. On Linux x86-32, these constants are defined with the values 8192 and 2048 respectively. The kernel doesn't resize an alternative signal stack. If the stack overflows the space we have allocated for it, then chaos results, e.g. overwriting of variables beyond the limits of the stack. This is not usually a problem because we normally use an alternate signal stack to handle the special case of a standard stack overflowing. Typically only one or a few frames are allocated on the stack. The job of the sig-seg-v handler is either to perform some cleanup and terminate the process, or to unwind the standard stack using a non-local goto. The SS flag field contains one of the following values. SS on stack, this is the flag is set when retrieving information about the currently established alternative sig stack. It indicates that the process is currently executing on the alternate signal stack, attempting To establish a new alternative signal stack while the process is already running on an alternative signal stack results in an error. Okay. As disable returns an old signal stack, this flag indicates there's no currently established alternative signal stack. When specified in sig stack, this disables a currently established alternative signal stack. Listing 21.3 demonstrates the establishment and use of an alternative signal stack. After establishing an alternative signal stack and a handler for sig-seg-v, the program calls a function that infinitely recurses so that the stack overflow and the process is sent a sig-seg-v signal. When we return to the program, we see this. So we say, hey, ulimit your -s is unlimited. What is that? And ulimit s flag. Okay. What does ulimit -s unlimited? Probably file descriptor limit. Stack size limit. Okay. Makes sense. Okay. So we say, hey, my ulimit for the shell is now unlimited for stack size. And then I'm going to run my signal stack, signal T stack. And it says, hey, top of the standard stack. Oops, I'm on the wrong page here. My bad. Down here, top of the standard stack is near that address. Alternative stack is at some other address. Call 1. Top of the stack is near that. Yep. It's in the same space. Many intervening lines of output removed. Call. So it's getting to the fours. Huh. Okay. Then it caught signal 11 segmentation fault, and then it set the top of handler stack near that. In this shell session, the ulimit command is used to remove any limit stack resource limit that may have been set in this shell. We explain the resource limits in section 36.3. Then here's the program for using signal T stack, or sig alt stack. Sig alt stack. Setting the SA sig info flag when establishing a handler with sig action allows the handler to obtain additional information about a signal. When it is delivered, in order to obtain this information, we must declare the handler as follows. Okay, so this is getting more information than just the signal number. So you get the signal number, you get sig info. Sorry, I'm on the wrong page again. Here. So you get the signal, you get sig info T structure, and a context, a U context. The first argument sig is a signal number. As for the standard signal handler, the second argument sig info is a structure used to provide the additional information about the signal. We describe the structure below. The last argument, U context, is also described below. Since the above signal handler has a different prototype from the standard signal handler, C typing rules mean that we can't use the SA handler field of the sig action structure to specify the address of the handler. Can't use this. Okay. Because that's specific prototype. That makes sense. Instead, we use an alternative field, SA sig action. In other words, the definition of the sig action structure is somewhat more complex than what was shown in 2013, and full the structure is as defined. It's a union between two different types of handlers. It's fine. Yeah. Following defines make the union fields look like simple fields in the parent structure. Okay. The SIG action structure uses a union to combine the SA SIG action and SA handler fields. Most of the Unix implementations similarly use a union for this purpose. Using a union is possible because only one of these fields is required during a particular call to SIG action. However, this can lead to strange bugs if we natively expect to be able to set the SA handler and SA SIG action fields independently from one another. Perhaps because we reuse a single SIG action structure in multiple SIG action calls to establish handlers for different signals. Here's an example of the use of SA SIG info to establish a signal handler. So we have struct SIG action act, SIG empty set, then we add the handler to SIG action, and then we say I want more info, so I set the flags, and then we call SIG action. Makes sense? For complete examples of the use of the SA SIG info flag, see listing 22.3, page 462, and listing 23.5, page 500. The SIG info T structure. The SIG info T structure passed as the second argument to a signal handler that is established with SA SIG info has the following form. Wow, that's a big one. It gives you lots of info. So you get the signal number, you get a signal code, I don't know what that is. You get the trap number, don't know what that is. Company data from SIGQ, process ID of the sending process, that's useful. Real user ID of sender. Error number, generally unused. So you can do authentication with the real user ID. Address that is generated, that generates signal. Override count. Timer ID. Banned events. File descriptor. Exit status for signal. User CPU time. System CPU time. Great. The POSIX source feature test macro must be defined with the value greater than or equal to this number. In order to make the declaration of the SIG info T structure visible from signal.h. On Linux, as on most Unix implementations, many of the fields in the SIG info T structure are combined into union, since not all the fields are needed for each signal. See bit SIG info for details. Upon entry to a signal handler, the fields of the SIG info T structure are as follows. Okay, lots more information about SIG T, and then we get a table about values, return the code field, and then we have a section on interrupt and restarting of system calls, and then we're done. All right, 6:30. I think I can get through this before 7. Alright, let's just speed read this. Upon entry to a signal handler, the fields of the SIG info T structure is set as follows. SI SIG no, this field is set for all signals. It contains the number of the signal causing identification of the handler, that is the same signal as the SIG argument of the handler, so it's redundant. They really didn't need to include the signal number as a separate argument. SI code, this field is set for all signals. It contains a code providing further information about the origin of the signal as shown in table 21.2. SI value, this field contains the accompanying data for the signal sent via SIGQ. We describe SIGQ in section 22.8.1. 22.8.1. So this is when you get into real-time signals, yeah. So you can do real-time signals, and you can set additional data with the signal. PID for signal set via kill or SIGQ. This field is set to the process ID of the sending process. UID for signal sent via kill or SIGQ. This field is sent to the real user ID of the sending process. The system provides the real user ID of the sending process because that is more informative then providing the effective user ID. We got a spammer here. Boop. Where are we at? SI error no. If this field is set to a non-zero value, then it contains an error number, like error no, that identifies the cause of the signal. This field is generally unused on Linux. SIGADDR, this field is set only for hardware-generated SIG bus, SIG segv, SIG IL, and SIG FPE signals. For the SIG bus and SIG segv signals, this field contains the address that caused the invalid memory reference. For the SIG IL and SIG FPE signals, this field contains the address of the program instruction that caused the signal. So SIG IL is a legal instruction. FPE, I forget what that is. The following fields, which are non-standard Linux extensions, are set only on the delivery of a signal generated on expiration of a POSIX timer. SIG timer ID, the field contains an ID that the kernel uses internally to identify the timer. This field is set to SIG overrun. This field is set to SI overrun, sorry. This field is set to the overrun counter of the timer. Boop. The following two fields are set only for delivery of a SIG IO signal. SI band, this field contains the band event value associated with an IO event. Version of glibc up to so-and-so. This band was typed as int. SIFD, this field contains the number of the file descriptor associated with the IO event. This field is not specified in SUSV3, but is present on many other implementations. Following fields are set only for the delivery of a SIG child signal. SI status, this field contains either the exit status of the child or the number of the signal sent to the child. Okay, SI U time, this field contains the user CPU time used by the child process. This field contains SI S time, this field contains the system CPU time used by the child process. Great. The SI code field provides further information about the origin of the signal. Using the values shown in table 21.2, not all of the signal-specific values shown in the second column of this table occur in all Unix implementation and hardware architectures, especially in the case of 4 hardware-generated signals, SIG bus, SIG segv, SIG IL, and SIG FPE, although all these constants are defined on Linux and most appear in SUSV3. Note the following additional points about the values shown in table 21.2. The values SI kernel and SI SIG IO are Linux-specific. They are not specified in SUSV3 and do not appear in other Unix implementations. SI SIG IO is employed only in Linux 2.2 from kernel 2.4 onward. Linux instead employs the poll constants shown in the table. SUSV4 specifies this psiginfo function whose purpose is similar to psignal. The psiginfo function takes 2 arguments appointed to the siginfo structure and a message string, prints the message string into standard error, followed by information about the signal described in the siginfo T structure. The psiginfo function is provided by glibc since 2.10. The glibc implementation prints the signal description, the origin of the signal as indicated by the SI code field, and for some signals, other fields from the siginfo T structure. psiginfo function is new to SUSV4 and is not available on all systems. Okay, let's look at this table here. Values returned in the SI code field of the SIGINFO T structure. So the signal, any signal can generate these. So async IO. So I guess I didn't really realize like that async IO was implemented with signals. I guess how would it work otherwise? I guess you would go in if you were, your program says, hey, I'm gonna wait for one of these file descriptors to be ready, and then when one of them is ready, that ready check unblocks, and in the meantime the kernel just doesn't run your code. That's kind of like blocking IO though, right? Because when you do a read, if it's not available to read, it blocks. That's more just a multi-file descriptor read. So that's not how it works. So the idea is that you're going to be doing work. You're going to continue to run active on the CPU, the program, the thread, the task, or whatever. It's going to continue to run active on the CPU. And then when one of these file descriptors is ready, then you get a signal. You capture a signal using the SIGINFO T advanced signal handler, and then that tells you, hey, this thing is ready, and you're like, okay, I know what file descriptor is ready, I'm gonna go handle that now. And then you go and handle it, or you just mark the file descriptor as ready in some type of data structure that's shared with the handler, and you then return from the signal handler, and then there's some check in your main loop in your program that says, okay, now that I'm at a point where I want to start checking things, I can check those things. Maybe that's how it works. Use some type of atomic communication between the handler and the main thread. I'd be curious to see some implementations of low-level async IO code, so I'm sure that's coming in the later chapters. But in the meantime, it's good to know that there is a async IO signal code. As a kernel, which is sent by the kernel, e.g. a signal from terminal driver, message queue, a message arrival on POSIX message queue. Queue itself is a real-time signal from a user process. SIGIO. Okay, expiration of POSIX real-time timer. User process via tkill or tgkill. User process via kill. Okay. SIG bus, SIG child, SIG FPE, SIG ill, SIG poll, SIG IO, SIG SIG-V. SIG bus can generate all these bus types. SIG child, SIG FPE, it's a floating point error. So that is SIG ill, SIG poll, SIG IO, SIG SIG-V, and finally, I figured there'd be more than 2 SIG SIG-V codes, given how many ways that you can get a SIG SIG-V. Okay. SIG trap. Okay. The uContext argument. The final argument passed to a handler established. Yeah, what is this uContext thing? The final argument passed to a handler established with a SA SIGINFO flag uContext is a pointer to a structure of type uContextT defined in uContext.h. Substitute 3 uses a void pointer for this argument because it doesn't specify any of the details of the argument. This structure provides so-called user context information describing the process state prior to invocation of the signal handler, including the previous process signal mask and save register values, e.g. program counter and stack pointer. This information is rarely used in signal handlers, so we don't go into further details. Another use of uContext structure is with the functions getContext, makeContext, setContext, and swapContext, which allow a process to retrieve, create, change, and swap execution context, respectively. These operations are somewhat like setJump and longjump, but more general. These functions can be used to implement coroutines. Nice. Where the thread of execution of a process alternates between two or more functions. Substitute 3 specifies these functions, but marks them obsolete. Substitute 4 removes this specification and suggests that applications should be written to use POSIX threads instead. Like, just use threads. It's like, people like their coroutines. The glibc manual provides further information about these functions. Okay, last section here, I think, before the summary. Interruption and restart of system calls. This is something that is new to me, because usually I've only been able to do that with ptrace, where you can intercept system calls, or something like setcomp, where you can reject system calls. Yeah. Let's see what's going on here. Consider the following scenario. We establish a handler for some signal. We make a blocking system call, for example, a read from a terminal device, which blocks until input is supplied. While the system call is blocked, the signal for which we establish a handler is delivered, and its signal handler is invoked. What happens after a signal handler returns? By default, the system call fails with the error INTR interrupted function. This could be a useful feature since in section 23.3 we'll see how to use a timer, which results in the delivery of SIG alarm signal, to set a timeout on a blocking system call such as a read. Often, we would prefer to continue the execution of the interrupted system call. To do this, we could use code such as the following to manually restart a system call in the event that it was interrupted by a signal handler. If we frequently write code such as the above, it can be useful to define a macro such as the following. So basically it's just a while loop that'll call, as part of the condition, it'll call the syscall and check if its result is -1. If it is, and the error no, then we is equal to ENT, then we continue. And eventually, it's either going to be, So basically, like, call it, and chances are it's not going to be an error, and it's going to immediately exit the loop. It's going to be a while false, basically. And the chance that your first call, you actually did get an error, and the error was ENT error, then we retry it forever. And then we say, hey, if the count was -1, then we can handle the error. All right. Using this macro, we can rewrite the earlier read call as follows. The GNU-C library provides a non-standard macro with the same purpose as our no ENT error macro in unistandard.h. The macro is called temp failure retry and is made available if the GNU source feature test macro is defined. Even if we employ a macro like no ENT R, Having signal handlers interrupt system calls can be inconvenient, since we must add code to each blocking system call, assuming that we want to restart the call in each case. Instead, we can specify the SA restart flag when establishing the signal handler with SIG action, so that system calls are automatically restarted by the kernel on the process's behalf. This means that we don't need to handle a possible ENT-R return for these system calls. The SA restart flag is a per signal setting. In other words, we can allow handlers from sudden signals to interrupt blocking system calls, while others permit automatic restarting of system calls. System calls and library functions for which SA restart is effective. Unfortunately, not all blocking system calls automatically restart as a result of specifying SA restart. The reasons for this are partially historical. Restarting of system calls was introduced in 4.2 BSD and covered interrupted calls and wait and wait PID, as well as the following IO system calls: read V, write V, and blocking IOCTL operations. The IO system calls are interruptible and hence automatically restarted by SA restart only when operating on a slow device. Slow devices include terminals, pipes, FIFO, and sockets. On these file types, various IO operations may block. By contrast, disk files don't fall into the category of slow devices because disk IO operations generally can be immediately satisfied via the buffer cache. If a disk IO is required, the kernel puts the process to sleep until the IO completes. A number of other blocking system calls are derived from System V, which did not initially provide for restarting of system calls. On Linux, the following blocking system calls and library functions layered on top of system calls are automatically restarted if interrupted by a signal handler established using the SA restart flag. The system calls used to wait for a child process: wait PID, wait 3, wait 4, wait ID. The IO system calls read V, write V, and IOCTL when applied to slow devices. In cases where data has already been partially transferred to the time at the time of signal delivery, the input and output system calls will be interrupted but return a successful status, an integer indicating how many bytes were successfully transferred. The open system call, in cases where it can block, when opening FIFOs as described in section 44.7, various system calls uses sockets: accept for, connect, send message, send to, receive from, receive message. On Linux, these system calls are not automatically restarted if a timeout has been set on the socket using set sockopt. See signal manual page for details. System calls used for IO on POSIX: message queues, MQ receive, MQ timed receive, MQ send, and MQ timed send. System calls, basically a bunch of stuff. And kernels before 2622. So and so always fail with the error EENTER when interrupted, regardless of the setting of the restart flag. Okay, more stuff that are blocking system calls are never automatically restarted. Bunch of stuff. Modifying the SA restart flag for a signal. The SIG interrupt function changes the SA restart setting associated with a signal. If flag is true, then a handler for the signal SIG will interrupt blocking system calls. If flag is false, then blocking system calls will be restarted after execution of its handler for SIG. The SIG interrupt function works by using SIG action to fetch a copy of the signal's current disposition, tweaking the SA restart flag, and the returned old account structure, and then calling SIG action, old action, SIG action once more to update the signal's disposition. SUSC4 marks SIG interrupt obsolete, recommending we use the use of SIG action instead for this purpose. unhandled stop signals can generate EENTER for some Linux system calls. On Linux, certain blocking system calls, such as EENTER, system calls can return EENTER even in the absence of a signal handler. This can occur if the system call is blocked and the process is stopped by a signal and then resumed by delivery of sig continue signal. The following system calls and functions exhibit this behavior. In kernels before 2624, poll also exhibited this behavior. Sleep. The upshot of this behavior is that if there is a chance that our program may be stopped and restarted by signals, then we may need to include code to restart these system calls, even in a program that doesn't install handlers for the stop signals. Summary. In this chapter, we considered a range of factors that affect the operation and design of signal handlers. Because signals are not queued, a signal handler must sometimes be coded to deal with the possibility that multiple events of a particular type have occurred, even though only one signal was delivered. The issue of reentrancy affects how we can update global variables and limits the set of functions that we can safely call from a signal handler. Instead of returning, a signal handler can terminate in a variety of other ways, including calling exit, terminating the process by sending a signal, performing a non-local goto. Using sig set jump and sig long jump provides a program with explicit control of the treatment of the process signal mask when a non-local goto is performed. We can use signal stack to define an alternative, so sig alt stack to define an alternative signal stack for a process. This is an area of memory that is used instead of a standard process stack when invoking a signal handler. An alternative signal stack is useful in cases where the standard stack can be exhausted by growing too large, at which point the kernel sends a sig-seg-v signal to the process. The signal actions SA sig info flag allows us to establish a signal handler that receives additional information about a signal. This information is supplied via siginfo t structure, whose address is passed as an argument to the signal handler. When a signal handler interrupts a blocking system call, the system call fails with the error EENTER. We can take advantage of this behavior to, for example, set a timer on a blocking system call. Interrupted system calls can be manually restarted if desired. Alternatively, establishing the signal handler with a sig action SA restart flag causes many but not all system calls to be automatically restarted. Boop. Okay. It is 7 p.m. I'm going to start winding down for the evening, but I'm going to call this one done. Let's go to vim readme. Oops. Get out of here, vim readme. We are done with chapter 21. And you know what that means. It means that we're more than a third done with our chapters, at least. Not quite there yet on the page count. So this is going to be advanced features. Cool. Get status, get at all, get C, or I'll do get status first. We need a CPR chapter 2020 .get ignore to chapter 21. Then rm or get rm chapter 21 / build. We'll do -r, get status, get at all, status, get at all, get status, rmr chapter 21 build. Go away. Alright. CD chapter 21 make, get status, make clean, Okay, that's working now. Let's go ahead and say finish chapter 21. And then git push. And then what else are we going to do? T7 done. Which gives us 30, no, we're still 32% complete. Alright, we're not 33% yet. Chapter 22 will be 33% for sure. And that ends at what page? Let's see. Okay, that ends on page 478. Oops. Which will be officially 30 or 1/3 done after we finish this chapter. This chapter, oh cool, we get to revisit core dump files a little bit more. We did some core dumping in this chapter, but we get to look at that a little bit more. Special cases for delivery, disposition, and handling. Not going to be super interested in that, to be honest. Interruptible and uninterruptible process sleep states. Okay. Harper generated signals, synchronous and asynchronous signal generation. That one I'm going to be interested in reading. Timing and order of signal delivery. I guess that's kind of a little bit interesting. Implementing and portability of signal, don't care about that. Real-time signals, this is going to be interesting. Like the difference between real-time signals and regular signals. Waiting for a signal using a mask, sig suspend. Synchronously waiting for a signal. Fetching signals via file descriptor. Okay. Inter-process communication with signals, early signal APIs. I guess some of this would be interesting, but real-time signals is most interesting. The core dump stuff, of course. Order of delivery, Yeah, that's about it. So not a lot that I'm super interested in there, but after that time, I was supposed to have this done on Sunday, and it's Monday night, so it's gonna be going into Tuesday, because I wasn't on yesterday. So I'm falling a little bit behind here as far as my expected progress. But Tuesday I will definitely have signals done. Tomorrow I have a little thing in the morning after training that I have to do, but pretty much the entire day I can spend reading. So we will be getting into timers and sleeping tomorrow. And then process creation. I mean, the fork exec pattern I'm very familiar with, but I'm still kind of excited to get into some of the details here, because I don't think I've actually read this whole chapter before. But yeah, process creation, process termination, probably going to get done tomorrow. Assuming, well, maybe not. We'll see. But I'm mostly excited for those two chapters. So tomorrow, gonna get through signals, finish signals, get through timers and sleeping, and then maybe if we have time, process creation and termination. Cool. All right, well, I'll leave it there. Bam. All right, yeah, and tomorrow we'll have 1/3 of the book read with, sampling of the exercises complete. Just thinking about it, it is January 19th. So probably not going to be able to finish the book by the end of January, but maybe mid-February. That's what I'm thinking. But I mean, look how much progress we've made so far. That whole section there. It's a good amount of reading. It's 450 pages around. A very dense technical reading. So, all right, I'm gonna hop off here, and I'll be on tomorrow morning to resume reading on chapter 22.